Okay, today we are going to learn about basis and dimension. Before we talk about basis and dimension, we learn about linearly independent set and linearly dependent set. But you already read the definition, read the material, I think, because last assignment you mentioned about linearly independent set and dependent set. Okay, the definition of linearly independent set, we have R factor here. We have S contain V1, V2, and the VR. VR is a non-empty set of the factor. Then we have this equation Q1, V1, K2, V2 plus until KR, VR equals to 0 factor here. If we solve this equation, if we solve this system, for sure we have at least one solution. If you remember our first topic about homogeneous system. Okay, from here we have at least one solution, trivial solution, or we can say all the solution 0. If this is the only solution, I mean, if the solution only trivial solution, only 0 solution here, then set S is a linear independent set. But if there are other solutions, not only trivial solution, then set S is a linear dependent set. Okay, for the example, we have U, V, and W. The set U, V, W is linearly dependent. Why? Because we have this equation. It means we have K times U plus K1 times U, K2 times V, plus K3 times W equals to 0. We get solution K1 equals to 1, K2 equals to 2, and K3 equals to minus 1. So it means the solution of the system, not only a trivial solution. We have another solution. That's why we say set S is linearly dependent. If you check this, W is linear combination of U and V, right? If you change, if you move W to the right side, you get W equals to U plus 2V. It means W linear combination of U and V. Okay, the second example, we have IGK. Factor I 100, G 010, and K 001. And then you arrange the equation here, A1 BG plus CK equals to 0. 0 factor here. And then you have system, right? A1, sorry. A, B, and C, right? Equals to 0 factor. From this, we get the only solution is trivial solution, or A, B, and C are 0. This is the only solution. Since this is the only solution, so we conclude that the set S, I, G, K is linearly independent. We have no other solution. Okay, we have property here. We have set S with 2 or more factors. Our set S is linearly dependent if and only if at least one of the factor in S is expressible as a linear combination of the other factors for sure in S. Our set S is linearly independent if and only if no factor in S is expressible as a linear combination of the others factor in S. Okay, if you take a look at this, like I said before, from here we have W, our factor W here can be expressed as linear combination of factor U and factor V. That's why this set linearly dependent. But for the second example, IG or key, we cannot express I as linear combination of G and K. G also cannot express as linear combination of I and K. And so is for K. Cannot be expressed as linear combination of I and G. Okay, next property. A finite set of factor that contains 0 factor is linearly independent. Once you have set that contains 0 factor, so you can conclude that the set is linearly dependent. Okay, and then a set with exactly 2 factors is linearly independent if and only if neither factor is a scalar multiple of the other. Okay. If we have set S contain V1, V2, Vr in n space here, if R greater than n, then S is linearly dependent. So for the example, if we have R3, and then we have set S that contain 4 factors, so we can directly conclude that S is linearly dependent. Okay, later I give you the exercise. Is there any question? Linearly independent and dependent?
Not yet.
Not yet, okay. This is our main topic today, basis and dimension. What is basis? We have V is vector space and B is a set that contains V1, V2 until Vn. V1, V2, Vn is a factor in V. Then B is a basis for V if B span V and B is linearly independent. So you have to check two conditions here. First one, you have to show that B spans V and B is linearly independent. And then the dimension of vector space V is defined to be the number of vectors in a basis for V. For the example, if we have basis here, V1, V2 until Vn, so the dimension of the vector V here is n. Okay, if we have zero factor space, it means we have vector that contain only zero factor. So we conclude that the dimension of the zero factor space is 0. Okay, for the example, we have vector space R2 here, to space. And then we take U and V here, U1, 1, and V2, 3. You want to show that the set B, UV here, is a basis for R2. So the first one, we have to show that B spans V. And the second one, we have to show that B is linearly independent. If you want to show that the set B spans R2, so we have to show that an arbitrary vector S in R2 can be expressed as a linear combination of the vector in B, or linear combination of U and V, right? So we have X, Y equals to A times 1, 1 plus B times 2, 3. Wait. Oh, okay. I typo. This should be K1. Our scalar here, K1, and B, K2. Okay, solve this system. We have K1 equals to 3x minus y, and K2 equals to minus 2x plus y. It means B spans R2. Okay, maybe we can use our previous way. I mean, like your assignment, your answer of the assignment. From this equation, we have system K1 plus 2, K2. So what is our matrix A here? Our matrix A, the first row is 1 and 2, right? One, okay, 1, 2, A. And then the second row, we have 1, 3. Now, if you determine the determinant, we have a let's try. Okay, if we determine the determinant of A, we have not 0, right? 3 minus 2, 1. So it means the system is consistent for all K1 and K2. It means U and V spans R2. Okay, the second one, we have to show that our B is linearly independent. This one should be 0, not 0 factor. I typo again. Okay, if we want to show that the solution, the set B linearly independent, so the solution for the system is trivial solution. So we have K1, K2. Oh yeah, okay. Yeah, this is right. This one, our system, K1 times U plus K2 times V equals to 0 factor. The solution, only K1 and K2 are 0. Okay, from the previous result, from here, we have our system K1 or K1 plus 2K equals to X. And then we change X, Y into 0, 0. Solving the system, we have augmented metric here. We have, wait. Why so hard to move this 0 and then 0, right? We operate this augmented metric, we get K1, K2 is 0. Or from the previous result, we have K1 equals to 3x minus y. When x and y 0, for sure we have K1 equals to 0 and K2 equals to 0. So it means the solution of this system only trivial solution. So our B here is linearly independent. Okay, since our set B spans R2 and linearly independent, so we conclude that our set B here basis for R2. And dimension of R2, the number of factor in basis, we have 2 factor here. So we conclude that dimension of R2 is 2. Okay. Next example, we have standard basis. Okay, we have factor, 3 factor here, 1, 0, 0, 0, 1, 0, 0, 0, 1. We already proved, we already show that this factor span R3 and this factor also linearly independent. So we conclude that S is a basis for R3. This is standard basis for R3. Generally, if we have this one, we have A1 factor in Rn, A1 1 0 0 0, A E2 0, 1, 0, 0, 0. So our this component 1 only in I position. AI, the entry 1 only in I position. Okay, we have n factor here. So the set A1, A2 until En is a standard basis for Rn. So if we write in R4, we have, wait, our standard basis for R, oh, this. Okay, this one for n space. What about polynomial? If we have polynomial of degree n, our standard basis is 1, x squared, x cubed, x to the power 4, until x to the power n. So the dimension here, if you count this, 1, 2, 3, we have this n plus 1 factor. So be careful for the polynomial of degree n. The dimension is n plus 1. We have, if we want to find the dimension of Rn is n. So R4 dimension of R4 is 4. What about matrix? This one only for 2 by 2 matrices, vector space. We have M1 here, the entry 1 only in first row and first column. M2, entry 1 only first row, second column. M3, entry 1 only in second row, first column. And the last metric is this. Okay, all of the matrices in 2 by 2 matrices. Then we have the set S here. M1, M2, M3, M4 is a standard basis for M22. This one means a set of all matrices, 2 by 2 matrices. Okay, those the dimension of 2 by 2 matrices is 4. Generally, if we want to find the dimension of n by, wait, n by p times q matrices, what is our dimension here? Okay, maybe I ask you the simpler question. If we have 2 by 3 matrices?
2 by 3, 6.
6, okay. So from this?
P P times Q.
P times Q. Okay, great. Because we have a component or entry here for M2 times 3, so we have 6 component, right? P times Q, we have P times Q component or entries. Okay, any question up until here? No. The point is only you have to show that the vector set spans the vector space, and the vector set is linearly independent. Before exercise, we have property here. Okay, we have the vector space, and we have set of vector and vectors be any basis. So we have, if a set has more than n vectors, so it is linearly dependent. If you remember our previous property, if we have R vector in Rn, if we have R greater than n, so the set always linearly dependent. So it's from here. So it's for this set, V1, V2, Vn, any basis. Since this is basis, so this is linearly independent, right? So if we have vectors more than n, then the set vector linearly dependent. Okay, if a set has fewer than n vectors, then it doesn't span the vector space. The next theorem, all bases for a vector space have the same number of vectors. Note that we have many bases for a vector space. For the example, where is, okay, this one basis, and we have another basis, standard basis for R2. We have, maybe I can write this B2. This is standard basis. So we have 1, 0, and then 0, 1. We already mentioned, we already find 2 bases in R2. Still, there are many other bases. If you write this B3, I have, maybe I can write 1 minus 1. Okay, maybe I can write this minus 100. Okay, 5. This also a basis for R2. So many bases. But the number of factor in basis are the same. If you take a look at this, we have 2, B2, the cardinality of the B2 also 2, so it's for B3. So the property, the last property, say that All bases for a vector space have the same number of vector. That's why you can conclude that the dimension is the number of vectors in basis. Okay, this is the exercise we can answer directly, I think. Explain why the following sets of vectors are not base for the indicated vector space. Okay, if you take a look this, these are 2. But we have 3 vectors, right? Why these vectors are not base? What's your answer? Why? So it means doesn't hold one of the 2 condition of the basis, right? Doesn't span or not linearly independent. Which one?
Not linearly independent.
Not linearly independent, yes, because we have 3 factor here from the previous this one. If a set has more than n factor, we have dimension of R2 is 2, but we have 3 factor this. It means this linearly dependent. Okay, for the second one, we have vector space R3 here, but we only have 2 factor here. So it means U1, U2, which one doesn't hold for the condition of the basis? Doesn't span or linearly dependent?
Doesn't span.
Doesn't span, okay, that's right. The second property, if a set has fewer than n factors, then it doesn't span V. Okay, for the third one, we have polynomial of degree 2. So the dimension of P2 is?
Basis.
No, I mean this one, P2, the dimension of P2 is?
2.
No.
Oh, that means
Pn. If we have polynomial of degree n, so the dimension of the Pn, then you remember? Standard basis. If we have polynomial of degree n, so the dimension of Pn, n plus 1. Be careful. So the dimension of this 3.
3.
So the factor of the number of factor in basis supposed to be 3, but we only have 2 here. It means P1, P2 doesn't span P2. Okay, what about D? We have 5 matrix here and our vector space M2, 2. Do you remember the dimension of this vector space?
Yes, 2 times 2, 4.
4,
So,
okay. But we have 5 matrices here. It means
that doesn't hold the linear.
first one. Yeah, linearly dependent. Okay, which one of the following set of factor are base for R2? Oh, this one you have to, so these factors span R2 and linearly independent. Okay, later you have to show it. This one will explain why the following are the linearly dependent set of factors. Okay, all of this linearly dependent. The first one, we have U1 and U2 here, Why U1 and U2 linearly dependent? Because U2 is, do you remember the property? This one. A set with exactly two factors is linearly independent if, oh, sorry. Yeah. If only if neither factor is scalar multiple of the of the other. If you have a factor is a scalar multiple of the other, it means the two factor is linearly dependent. If you take a look if you take a look at these factors, you can write U2 equals to, can you find the relation U1 and U2? Or can you determine U2 as linear combination?
-5 U1.
-5. Okay, that's right. That's why this set U1, U2 linearly dependent. Or you can write this. It means U2 plus 5U1 equals to 0 factor. We have the solution of the system, not only trivial solution. We have K1 equals to 1, K2 equals to 5. So the set is linearly dependent. Okay. So B2, you have to show that one of the factor can be expressed as linear combination of the others factors. For C, we can easily check that P2 equals to 2P1, right? Yeah. P2 equals to 2P1. This one, B. What we have here? B equals to
-10.
negative A. Which of the following set are in R3 are linearly dependent? Okay, you have to check it. I don't remember which page here. So many exercise there. Okay, our material. Finished today. Is there any question about final exam?
Yeah.
When? This week or next week?
Next week.
Next week, okay. It's up to you. Maybe you want to take your final exam this week. I will prepare for the question. Okay. Is there any question? You can Stop the virtual room. Okay, thank you very much for your attention. Good luck and success for your final exam.
Yeah. Thank you.
Good morning or afternoon. So it's up to you.